Let's look at objects in freefall. Hello and welcome back to Fast Physics, where I come up with pretty strange scenarios to explain topics that we're exploring in physics together. Today we're talking about freefall, where there is no air resistance. That part's pretty important, so remember to keep it in your brain. Freefall is a special topic because even though we've been covering acceleration and the kinematic equations, freefall is caused by gravity, which kind of plays by its own rules. As we found out before in the video about acceleration, where the UFO was falling out of the sky, gravitational acceleration on Earth is negative 9.8 meters per second squared, where the speeds of objects falling towards the Earth increase by 9.8 meters per second every second that they're falling. But that's speed, which doesn't have direction because it's scalar. So when we're talking about the velocities of falling objects, we always need to keep direction in mind. Just like going down the y-axis of a graph gives us negative values and smaller values, objects falling down at negative velocities and gravitational acceleration is negative. Let's look at how important that can be by looking at a scenario. I put my spray gun straight downwards at my sister, with the water coming out of the nozzle at 3 meters per second. As it heads toward her, it accelerates at negative 9.8 meters per second squared, which is the gravitational acceleration on Earth, and it hits her after 1 second. What is the velocity of the water when it hits her? So you might be thinking that the second that the water hits her, its velocity will be 0 because it will have been stopped. Drop, 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 and then bam, it's still because it's encountering a surface. But that's not the case. When we're referring to objects in freefall, we always think about final velocity as the very instant before the object in question stops falling, or hits the floor, or whatever surface it's encountering. So the very highest speed it attains before stopping. So let's look at which kinematic equation we should use for this problem. If you don't know how to choose, be sure to check out my last video where I discuss how to use kinematic equations. From the question, we have the speed of the water coming out of the nozzle, which is initial velocity, negative 9.8 meters per second squared, which is acceleration, after 1 second, which is time, and we're looking for final velocity, so we have velocity, acceleration, and time. And so we can use the VAT equation, or final velocity equals initial velocity plus acceleration times time. We know that we're looking for final velocity, so we just have to substitute all our known values into the equation that we just chose. Let's keep direction in mind though. Since the water is traveling downward, both its final velocity and its initial velocity have to be negative. So just because the speed of the water is 3 meters per second doesn't mean that its initial velocity will also be 3 meters per second. Remember that the nozzle of the spray gun is pointing down, so the water, the second that it comes out, will be heading downwards too, so our number should be negative. So let's change 3 meters per second to negative 3 meters per second for our initial velocity, and substitute all of our known values. Negative 3 meters per second, negative 9.8 meters per second squared, and finally 1 second. So all we have to do now is solve the equation for final velocity. Negative 9.8 meters per second squared times 1 second. The 1 second cancels out so that we have negative 9.8 meters per second plus negative 3 meters per second, which gives us negative 12.8 meters per second, which is our final velocity and our final answer. If we were rounding to significant figures, 1 second only had 1 sig fig, so we'd have to round our entire answer to 1 sig fig, which would leave us with negative 10 meters per second. That's all good, but let's say that my sister decides to point her spray gun back up at me and shoots water at me. How does gravitational acceleration work on things that are moving upwards? I mean, gravity is definitely always acting on everything that's on Earth and pulling it towards the Earth. But obviously you can throw something up and it won't immediately fall down towards you. It'll head a little bit up before doing that. That's because gravitational acceleration is always constant. Even as you're throwing something up into the air, it's acting on it and slowing its velocity until it eventually reverses its direction and starts falling back down. So when things are being thrown into the air, this is how their velocity and acceleration look. On the way up, their velocities are positive but decreasing. At the very highest point, velocity is 0, and on the way down, the velocities are negative. So if my sister is spraying her spray gun up at me, and the spray gun shoots water out at 9.8 meters per second, let's track the velocity and position of the water as it moves up. After 1 second, it has a velocity of 0 meters per second because our first kinematic equation can tell us that. Our initial velocity of 9.8 meters per second is being added to acceleration times time, or negative 9.8 meters per second squared times 1 second, where the second cancels out, and we're left with 9.8 meters per second plus negative 9.8 meters per second, which just gives us 0 meters per second. Its position is velocity times time, our equation for displacement. So at 1 second, it's at 9.8 meters above my sister. This is the highest point that the water will be able to reach. After this, its velocity will be negative, which will cause its displacement to decrease as well. Don't just take my word for it though, let's keep using our first kinematic equation. To get the velocity of the water after 2 seconds, that's 9.8 plus negative 18.6, so the velocity is now negative 9.8 meters per second, and the water's position will be at negative 9.8 meters away from its previous position. velocity of negative 9.8 meters per second times 1 second. So it'll be right back where it started from the spray gun because its last previous position was 9.8 meters above my sister. 9.8 meters above her plus negative 9.8 meters gives us 0 meters, or as I said, right back on the spray gun and on my sister. The reason that we didn't just do negative 9.8 meters per second times 2 seconds was because the water wasn't moving at negative 9.8 meters per second for all of those 2 seconds. So we had to add the two displacements together to get our total change in position. This is the last video in this mini unit about one-dimensional movement and kinematics. So I hope you guys will continue to join me for two-dimensional kinematics. Thank you so much for watching, and definitely give me suggestions on how I could improve. Bye!